Hello, business students, and welcome back. What we're going to look at this week is exponential growth, specifically as it relates to inflation and also the time value of money. Now, you may remember from math or possibly in business class in the past the time value of money formula, which calculates compound interest. And I've listed the formula there as well as a bit of an explanation of what the variables are. The time value of money basically allows us to calculate what's called compound amounts, which means each time we accumulate more money in the account, or in the case of inflation, on the price of an object as time goes on, the next calculation of interest or increase in price and each subsequent calculation of those things is on the new value that was created by the increase from last time. So it tends to grow instead of linearly or the same amount each time. The growth rate is what's known as exponential, or the actual amount of growth increases as time goes on. As the principal amount gets larger and larger, the individual increases get larger and larger as well. Now over here, as I said, you can see the formula for the time value of money there. And there's four variables in the formula. We've got A, we've got P, we've got R, and we've got T. This is the number one, so that's certainly not a variable. A is usually the answer you're trying to look for. Basically, if I ask you, put X dollars into an account, what's left over in the future? A is the future amount. So what does the amount increase to? Or in the case of inflation, what does the price increase to over the course of time? P is the starting amount. So what did you start with at the beginning of time? And then A, as I said, is going to be the ending amount, or what's going to be there at the end of time. R is the interest rate. Make sure you always leave interest rates as decimals. So you'll often note that they're expressed as percentages. So make sure you divide them by 100 before you put in the equation, or you'll end up with some crazy numbers there. And then this exponent T up here is the amount of time, which generally is years. But since most interest compounds monthly or even more than that, the T value can be adjusted a bit. We're just going to look at annual things for this lesson. So we're going to do a couple examples that use annual interest just to kind of get through the concept while we don't have the luxury of a classroom. And I'm just going to move some people out of here because they're getting in the way. Here we go. And I want to get to the first question, which is a basic savings account type question. I'm sure you've done questions like this in math. If you took BBI 2.0, a grade 10 introduction to business, with either myself or Mr. Lovett, you definitely would have done some questions like this in the past. So let's just go through a basic one. I generally find the best way to start one of these questions is to write down everything I know. I know that there's four variables that I'm trying to find. Or I should say, I'm trying to calculate A, and I'm going to be given the other three variables. So let's write down what those variables are first, because we have P, we're going to have R, and we're going to have T. P, again, is the initial amount. So according to this question, I put $6,000 into a savings account, so that must be my initial amount. Since the $6,000 was put in the past, and the question's asking me what's going to be in there in the future after 10 years, right? So this is going to be the value of A that we're trying to find. And P, R, and T are going to help us get there. R is the interest rate, which says 3% annually. But as I said, always divide these by 100 before you put them in the formula, because the percentage going in the formula is not going to give you the right answer. But that'll give me an interest rate of 0.03, which I'm sure most of you guys recognize as the same as 3%. And then finally, T is the amount of time. Well, according to the question, it's going to be after 10 years. So I'm going to set T as 10. Now, my next job is to basically just punch these values into the formula, right? So I've got A equals P, 1 plus R to the exponent T. Now I'm just going to put these numbers directly in there, right? So P is going to become 6,000 because P is 6,000 over here. 1, well, that's the number 1. Plus R is 0.03. And then to the exponent T is 10 years. So I'm going to put a little exponent 10 on there. All right, looking good. Next, before I continue, I want to do my BEDMAS and make sure I add those two things in the brackets up first. I'm not really sure why I put a decimal point there. Sometimes I just like to add decimal places in because I feel like it. Now, before we put this in the calculator, I want to show you why this formula makes sense in the end. Basically, 6,000 times 1.03, if we hadn't put the decimal there, would just tell us what 3 more percent on 6,000 are. So 6,000 times 1.03, if we ignore the exponent, is basically a 3% increase on 6,000. Putting the 10 there means that the 1.03 actually gets multiplied 10 times. So 6,000 gets multiplied by 1.03 once. That's going to give you a number a little bit bigger than 6,000. But consider that there are 10 more, or I should say 9 more brackets with 1.03s in after due to that exponent 10 on there. So it's like increasing that amount by 3% 10 times. And each time you calculate the new 3% addition on, the next calculation of 3% is going to include what was added last time, which is the whole idea of compound interest. Without that exponent there, then it's not compound. And the world works on compound interest and compound values. So we're going to put that in the calculator. Okay, so when you're calculating these, generally the easiest way to do it is to just punch it in the calculator as it looks, especially if you have a scientific calculator that can handle all sorts of crazy decimal values. It's going to save you a lot of time, especially since the calculator is perfectly capable of doing bed maths, so you can avoid having to do it yourself. I don't know how much you guys love it. So when you punch in the calculator, and I'll put the calculation up there for you, looks like I end up with $8,063.50. Which isn't really too bad if you think about it. Put $6,000 away, don't touch it for 10 years, and you end up with an extra $2,063 on top of what you started with. Now, of course, a 3% interest rate on a savings account is an astronomical interest rate. And if you have any money and someone offers you 3% interest on any savings account, take it, because savings accounts, I mean, maybe 20, 30 years ago had 3, 4, 5% interest rates, but generally speaking, your savings account interest rate these days are somewhere between 0 and 0.5%, or about a sixth of this. Thanks, financial system. In example 2, we're going to use the exact same theory, but apply it to the concept of inflation. Inflation works exactly the same way as compound interest. Each year the price increases, the next year's price increase is going to be applied to the new price that was created by inflation from the last year. So again, the price on things increases at an exponential rate because they're increasing on the increases that have already happened. So again, same deal, let's put PR and T in here. Okay, even though this isn't interest in a bank account, we can still use the same formula. Now, in this case, we're looking at a postage stamp that starts at 2 cents. So I'm going to start that at 0.02. So in 1900, a postage stamp cost about 2 cents, or exactly 2 cents. Obviously, the price on postage stamps has increased considerably. If you already know what the price on postage stamps is today, you're going to be able to figure this question out without having to do too much math. But let's do it the mathematical way and come out with the same price that we have today. R is, in this case, going to be the inflation rate, which is the 3.24% that's listed. And again, just as I said all the time, make sure you divide that by 100, so you end up with 0.0324. The last one is T, which is the amount of time. Now, we're talking about the price change since 1900 to 2020. So that is a 120-year waiting period. Quite a bit, obviously, that we have to consider. A lot of time for the price to go up. And what you'll probably notice is that this very long period of time is going to cause the price to skyrocket over the course of 120 years. All right, either way, guys, we're going to put the equation in just as we have it before. So A equals P1 plus R to the exponent T. Okay, looks good. Now the principal this time is going to be 0.02 or 2 cents, the starting price there. 1 plus 0.0324 to the exponent 120. Again, I'm just going to simplify what's in the bracket here just to save me a bit of a headache. 0.2, 1.0324 to the 120. Now, it's probably not going to come out to the exact price of the postage stamp today, but I've planned it so it should be pretty close. Times bracket 1.0324, bracket exponent 120, and I'm going to end up with 91.8 cents, or 92 cents, 0.92. That's quite the increase in price. It's funny how a 3% increase per year can lead to the price like almost being multiplied by 50. That's due to the fact that compound interest over very long periods of time really does result in a much larger increase in the value and the cost of things than would otherwise be without that compound interest. All right, that's the end of today's primer on exponential growth. Stay tuned. The next video will be about the week's market summary.